This is Jason Molesky. In this example, we'll take a look at how random assignment works in an experimental design. This year, the high school has enough budget money to compare the online SAT course with traditional classroom instruction. 50 students have agreed to participate in an experiment comparing two instructional methods. Our problem is to describe how we randomly assign 25 students to each of the two methods, online or traditional. We'll want to take a look at how we do it using 50 identical slips of paper, how we do it using technology, and how we do it using Table D. Perhaps the simplest way to go about assigning these treatments is to use the hat method. So what we can do is write each subject's name down on one of the slips of paper, put all those slips in a hat, and mix them thoroughly. Then we can draw them out one at a time until we have 25 slips. Those 25 students would take the online course, while the remaining 25 students would take the classroom course. Alternatively, we could write online on 25 of the slips and classroom on the other 25 slips, then put those paper in a hat and mix them well. We could have students come up one by one and, without looking, pick a slip from the hat. This guarantees 25 students per group with the treatments assigned by chance. We could also use technology to assign our treatments. So we could give numbers 1, 2, 3, and so on all the way up to 50 to the subjects in alphabetical order by last name. Then we could use our calculator's randint command or a computer's random number generator to produce numbers between 1 and 50. The first 25 different or unique numbers that are chosen would select the students for the online course. Remember, we have to ignore repeats when they come up. The remaining 25 subjects would take the classroom course. Finally, we could assign this using Table D. We could use the two-step process from random sampling to do the random assignment. So to do this, we'd have to start by labeling all of the individuals in the class. Since we're using a random digit table, we'd have to give 2-digit labels to each individual. 01, 02, 03, and so on up to 50. Then we'd randomize. Could go to a line of Table D and read 2-digit groups moving from left to right across the row. The first 25 distinct labels between 0 and 50 that we encounter would select the online group. Remember, we'd have to ignore repeats, and we'd also have to ignore any numbers that fall outside of the 0, 1 to 50 range. Finally, the remaining 25 students would take the classroom course. And like I said, we'd ignore repeated labels and groups of digits from 51 to 00.
And before you do 59, what are we trying to avoid here? Confounding. And we achieve that by random assignment. So if you miss random assignment at the very beginning of an experiment, it's like building a house on sand, okay? There's no foundation, and it will fall down. It has no merit to it, okay? So this is the foundation here. And remember last class period what I told you about when you're writing the randint things or using Table D, that you have to explain it as though you're talking to somebody who's never seen this before. So some of you are not going to like being this detailed. You're going to want to say like, duh, figure it out, 01 represents this. But remember in the Gettysburg Address, what was the first word? 4. Okay, what digit in the random digits table would give you 4?
001.
001. That is not intuitive to most people. Follow me? So you'd have to spell out 001 represents the first word in the Gettysburg Address. 002 represents the second word in the Gettysburg Address, and so on. Okay? Same thing here. 01 would represent the first person, and so forth. And, yeah. Okay. Now try number 59, right? Things I'm going to outline here is amplified here. And you're going to unpack everything on here. Okie dokie? All right, so go back to this slide here. So the first thing is comparison. Okay. 2 or more treatments. Okay. What's the treatment in the amoxicillin? Well, the amoxicillin is a treatment. Amoxicillin. Okay. It says use 2 or more treatments. How would we do that in this case?
Placebo.
A placebo. Okay? So a placebo would be that would be the second treatment. And all a placebo is just a sugar pill. It looks like medication, but it's not. Okay? And the people don't know that if they're taking a placebo or not. Okay? So that's the first one. Random assignment, which is what we just talked about. Number 59 addresses this, so this is important. If you don't do random assignment, what might happen? Confounding occurs, and it kind of slips in there unnoticed, and bad things happen. Okay? Third thing is control. Let's go back to the birdie example. The duckbill, is that what they're called? Duckbill? Crossbill. Crossbill bird, something like that. What was one of the confounding variables that I mentioned? Predators. So suppose we close off these birds and we protect them from predators. We are eliminating variables that can affect the outcome. With me? Suppose we feed them or we make sure they have plenty of food. We're eliminating a variable that would be detrimental to their health. You with me? So that is called control. It's isolating or excluding variables so that you can really determine the question at hand. Okay? Replication. A lot of students think that this just means you do it over and over again. It's not what it means. Okay? Use enough experimental units in each group so that any differences of the treatments can be distinguished from chance. From chance. Okay? Between the two groups. Everybody circle the word chance. I'll tell you why that's significant later. So, our friend will give us a video here. You guys will try number 63.
In this example, we'll see what a well-designed experiment looks like. Does regularly taking aspirin help protect people against heart attacks? The Physician's Health Study was a medical experiment that helped answer that question. In fact, this study looked at the effects of two drugs, aspirin and beta-carotene. Researchers wondered whether beta-carotene would help prevent some forms of cancer. Now, the subjects in this experiment were 21,996 male physicians. There were two explanatory variables, or factors, each having two levels. Aspirin, yes or no, and beta-carotene, yes or no. Now these different levels are laid out in this particular chart. 1/4 of the subjects were assigned at random to each of these treatments. And on odd-numbered days, the subjects took either a tablet that contained aspirin or a dummy pill that looked and tasted like the aspirin but had no active ingredient, a placebo. On even-numbered days, they took either a capsule containing beta-carotene or a placebo. There were several response variables. The study looked for heart attacks, several kinds of cancer, and other medical outcomes. After several years, 239 of the placebo group, but only 139 of the aspirin group had suffered heart attacks. This difference is large enough to give good evidence that taking aspirin does reduce heart attacks. It did not appear, however, that beta-carotene had any effect on preventing cancer. Now let's explain how each of the 4 principles of experimental design was used in this study. Now you'll recall the 4 different principles are comparison, random assignment, control, and replication. For comparison, we note that researchers used a design that compared both of the active treatments to a placebo. For random assignment, we note this was used to determine which subjects received each of the 4 treatment combinations. This helped ensure that the treatment groups were roughly equivalent to begin with. The experiment used subjects of the same gender and occupation, and all subjects followed the same schedule of pill taking, so this experiment does have an element of control. And for replication, there were over 5,000 subjects per treatment group. This large number of subjects helped ensure that the difference in heart attacks was due to the aspirin and not due to chance variation in the random assignment. For some additional practice in identifying well-designed experiments, try exercise 63.